Hey guys, so welcome to session 2 of Introduction to Data Science. In the last video, we talked about the end-to-end data science development process, and today we will be looking at the different types of data science problems. The most common types of data science problems are regression and classification, right? If you go to any website, you will see that, regression and classification have a wide variety of algorithms available to solve these problems. Then comes time series forecasting, which is another very important domain of data science. Recommendation systems are being widely used by companies such as Amazon and Netflix to make recommendations to users, and even like Google News, if you scroll the news, what news should be shown on the top, that is being driven by these recommendation systems at the back end. You have A/B testing, where you want to see what buttons to show on your web page so that you can optimize and maximize the number of clicks, for example, that a user does. Then is optimization, right? Optimization is basically if you have a constrained set of resources, say, you have one truck and you want to fill in as much as much weight of material that you can, but all the boxes are of different sizes. So how do you optimize that so that you can transport the maximum amount with the limited space that you have? So that's a kind of an optimization problem, right? So I will be going over all of these in much more detail, but today's session is just to give you a flavor of what these mean so that you can talk about these and show people that you have just started in data science and you know what these basic types of problems mean. What is a regression problem? A regression problem is that in which we are trying to predict something like a continuous value. Say we are trying to predict income of a person, and we know attributes such as his education, his age, the years of work experience that he already has, etc. We look at different people, right? And the data points here, for example, you see a 2D plot. The x-axis is education and the y-axis is income, which we are trying to predict. This is the historical data which is represented by the dots here. And the question mark is, say we know that the education of a new person is of a certain number of years. What would be his income? What a regression problem or what a regression algorithm instead does is that looking at the historical data, it understands what is the pattern in the data, and a linear regression more specifically fits a line to it using a least squares minimization, least squares objective function. So simply put, in a regression, you are trying to regress the points onto a line. Like a regression is for a continuous variable like income, where you don't have categories. Classification problem is, on the other hand, only for categories. You're trying to classify, say, whether it's a yes or a no, it's a fraud or it is not a fraud, and so on. In a classification plot like this one, this is basically a curve for a logistic regression, right? But more generally, I mean here that you have two categories on the y-axis. You have high income and you have low income, and the x-axis can be continuous, the number of years. This can be 12.6, 12.7 and so on. So say you have 12 years of education plus 6 months of additional education. So that would be represented as 12.5 on this x-axis. Now the algorithm fits to this particular data, so that whenever you get a new question mark, right, you get a new question mark of, say, this new person has this much education, should his income be low or should it be high? So you are predicting categories. This is a classification problem where you're classifying what bucket that person or that entity lies in, right? Here I've taken the example of predicting income from education for both regression and classification, but this can be multifold, right? In a time series problem, we are trying to forecast what the next period would look like for a certain attribute. Here, for example, I've taken savings on the y-axis and time on the x-axis because it's a time dependent variable, right? In a forecasting problem, we look at historical data of time series and try to predict what the next period could look like, and the period here could be a quarter, it could be a month, it could be a week, and so on. Here your y variable might be dependent on other variables, so savings might also be dependent on income, for example, on whether it's a family or it's a single individual, right? These are all contributing factors to what a savings would look like. So all those factors can also be incorporated in a time series problem, and this is just a very simplistic representation of what a time series looks like. But this is called a univariate time series. We can have multivariate time series. So we will go into all these different concepts later on. Now we come to recommendation systems, right? Recommendation systems are basically about transaction data or data of a certain group of people, right? And we are trying to recommend to a particular user what his next purchase should be, what his next movie should be, and so on. So we have historical data of a bunch of people, and for a new person or for an existing person, we are trying to predict what his likely next purchase or his next movie should be, right? So here you can see, say this is kind of a market basket analysis where a user has apple, milk, and chocolate in his basket, or he has bought these items. Another user has only apple and banana, and another user, say, has apple and egg, right? Looking at all of these users, we can say that if a person has say apple and milk in his basket, right, what his next purchase or what is he most likely to buy next. So we can automatically recommend to him that you have not put this in your basket, in your cart, and would you want to buy this? So that's kind of a recommendation problem as well. That's called association mining in this particular example of market basket analysis. A/B testing is the next one, is about basically we have two versions of a page and we want to see whether the new version will appeal more to users and they will be more likely to, for example, click on it, right? So here the metric that we are looking at is the click-through rate, but the metric that we want to optimize can be another metric like the duration that the person is staying on the page. Here we have a control group where the experimental condition that is called is not applied. So the page is kept as is, and in the test group, the experimental condition is applied. So here you can see a click button, right? And these two versions are shown to almost identical group of people, not to the same group of people, but to two different groups who are identical in most of their attributes, right? So here I've denoted blue person as someone having, say, a different gender, and three people of a different gender than that person, and similarly here. So for example, in this case, the gender distribution is the same. Similarly, if we are looking at, say the click button is about buying a subscription, we would also want to look at the income distribution of these two sets of people, because that would definitely affect how many people are likely to click on it, right? So controlling for all of these factors, the only difference then that remains is this new feature which has been added on this version of the web page. And then from that, we do some statistical testing and infer that this is a better page and we go ahead with it. Or if it is not a better page, then we keep the current page and go ahead with it. Next problem is the optimization set of problems that I briefly mentioned. It's about, say, a truckload optimization. You have a truck, you have a limited space. How many boxes would you want to load to that truck so that you are able to transport the maximum weight, right? If space is the constraint and weight is the variable that you're trying to maximize. So this is a kind of an optimization problem. There can be route optimization problems, say for Amazon deliveries, right? And etc. So Amazon might want to decrease its cost of delivery. So it might want to ask its drivers to take a particular route so that they are not traversing routes that are longer, but the most optimum routes, and they are able to save their costs and optimize their savings and their income in the process. So guys, this was all about the different types of data science problems. In the next video, we will go over each of these problems one by one and look at the different terms and terminologies that are involved. And then we'll be done with our introduction to data science series. Post that, I will be going into the depth of each of the algorithms that I mentioned in the first video, and I'll go over how they work and what kind of tools and techniques, like say particularly in Python and R, the different kinds of methods that you can employ to solve these problems. Hope you like this video. Please like, share and subscribe to our channel. See you next time.